Hi everyone, today I'm going to make presentation regarding analysis of pressuremeter test, and we are going to look the pressuremeter test from design point of view, conceptual. So let's look outline. We are going to discuss about basic knowledge of the pressuremeter test. We are going to look analysis at pressuremeter test from design point of view. That means assessing pressuremeter modulus, rebound modulus, yield pressure, limit pressure, coefficient of earth pressure at rest, as geotechnical engineer using it every time to assess horizontal stresses, and Young modulus. This presentation is not going to discuss about analysis from tester point of view and how to calculate calibrations, how to make corrections and build in the curves. This presentation also is not going to discuss how make preparation of equipment, so how to carry out test itself, because for this reason or for this I need like literally equipment which I don't have, unfortunately. So what is pressuremeter test? Pressuremeter test designed and made, or pressuremeter equipment, to assess compressibility of the soils, modulus of the soils, and definitely how you carrying out like pressuremeter test. You're making the hole, placing your probe, inflating your probe, and looking for stress-strain relationship on this curve. There are different types of pressuremeters and classifications. Doesn't matter how you're going to call it, based on method of placing your probe. So you have pre-bore pressuremeter. So what you're doing, you drill the hole, place your probe, and start inflating it. The second type of pressuremeter is self-bore pressuremeter. What does it mean? So probe itself contains equipment which can borehole can be drilled. And what's the main difference between pre-bored and self-bore pressuremeters? In self-bore pressuremeters, you don't have generally, if it's done properly, gap between your probe and your borehole walls. So it's immediately start pushing your soils or testing your soils. Pushed in pressuremeter, it's a bit different. So if you have very loose or very soft materials, you just can push in your probe. In this case, again, you don't have gap between your pressuremeter probe and soils, but in this case, you a little bit sharing your soil during penetration your probe itself. So missing some part of the curve if you compare it to self-bore pressuremeter. Based on number of cells you're using a probe. So you have monocell, so you have only one cell inflating, and that's it. You don't have another cells. You have tricell. It's originally in all pressuremeter theory was based on tricell guard cells. What does it mean? Let me show you guys. So you have probe itself. I'm not going to give you in detail, so just conceptual approach. And you have guard cells above and below your probe. So when it's inflating, you get every time flat edges of your pressuremeter probe, and you assume it's all cylindrical shape. When you have monocell, it's not exactly. In monocell, when you inflate and you have rod and your probe, so it's a little bit getting like that. I'm exaggerating a little bit, but you don't have literally cylindrical shape. So this advantage, disadvantage of monocell, but people using it and like make some assumption, you can get your parameters. And based on measuring of deformation, so you can measure diameter literally. So you have LVDT inside the probe, and you measuring specific spot how the diameter changing, or you measuring volume of your liquid going inside the probe, and generally it may not take some pressure meter. And based on applied pressure, sometimes you can classify high pressure, low pressure, or you can use pressure meters, or sometimes they're called dilatometers if you're using it inside the rock and bedrock, okay? Today we are going to discuss only Menard and Texan pressure meters, pre-board Menard Texan pressure meters, okay? Just keep in mind what's the difference between Menard and Texan, and this is very important. Menard, it's you applying equal pressure increments and you watching what happening with deformation. In Texan pressure meter, you apply equal volume increments and looking how change pressure or response, how soil responding. Now, some of people saying, oh, Texan pressure meter could be used also with equal pressure meter increments. Yes, theoretically. In practice, no. Like you can do it, but guys, it doesn't work very well. So if you start doing some experiments and trials, but generally it doesn't work very well. Keep in mind, and again, I would like to point these very important issues. Menard and Texan measuring volume change rather than diameter. So in why I'm just mentioning, because in many reports you can see when people use Menard or Texan, they are axis for measuring deformation. They're using relative changing of your diameter, delta R to R initial. Guys, it's pure math. You don't measure it. Rather than, for example, you have different like oil pressure meter or something, and you have literally LVDTs built inside your probe, and definitely using or measuring diameter in this case. Texan Menard doesn't do that. Now, I just would like to talk a little bit your design of pressure meter test location. I don't speak about location of borehole. I speak about the depth. So in many cases, engineers say, okay, make pressure meter test every 3 meters or every 2 meters. Doesn't matter what designer is going to decide. My opinion, it's not the best practice, and the reason why behind that, if you're doing this way, you can bump into transition zones between the layers. And I don't know personally what to do, especially when you're doing big project and you need parameters for specific layers. So if you're doing like every 2-3 meters, you are going to bump into transition zones, and I don't know what to do with these numbers. Example, I'm going to show you example. For example, you drilled borehole, investigation, geotechnical boreholes, and you found out in this borehole you have 3 meters of fill. You have from 3 to 7, let's say sand. From 7 to 15, you have clay, and from 15 to 19 meters, let's say silty sand. So if you're going to do, let's say every 3 meters example, yes, so what is going to happen? One test, 3, then 6, then 9, 12, 15, 18, and that's it. So it's what you can do. Now, in what happening? Test at 3 meters and test 15 meters, and almost I can say test in 6 meters also is going to be close to transition zones. So later stages, how are you going to place it inside your model? If you have 3 layers or 4, you have here 1, 2, 3, 4 layers. So what are you going to do with these results? I have no idea. So my suggestion, you can do 1.5, then you're going to do 5 meters, then 9, then 13, and let's say 16.5. And how to do it? Very simple, guys. You just keep on. Generally, in 90-95% of projects, you never ever carrying the pressure meter test at the same borehole when you carrying out SPT, investigation, geotechnical boreholes. That means you have to drill, you will find your layers, and then next step, whoever is going to go to carry out Pressuremeter test is going to do Pressuremeter test in proper locations. Okay, and definitely you need to write down groundwater table. We are going to discuss maybe later, not this part 2 of this Pressuremeter analysis. I'm going to discuss about this one. Now I just would like to show you conceptual output in Pressuremeter test. Pre-board Pressuremeter test, it generally looks like that, depends of axis you're going to use. For example, in left picture it's like vertical, it's volume, and horizontal axis X is like abscissa, it's like pressure, and on the right side just opposite. Okay, and this on self-boring Pressuremeter. Now I just would like to show you, you can see you missing initial part of these curves because no gap between your borehole and your probe. We are going to discuss it a little bit later. Okay, so conceptually you have 3 phases, 3 stages during your Pressuremeter test. How to find these 3 stages phases? You make tangent line to linear elastic zone, kind of, to your Pressuremeter, and you find 2 points which sitting on this straight line, and you have 2 points divide your Pressuremeter result into 3 phases. Phase number 1, actually probe inflated in air or in drilling mud. That means no contact between your soils of borehole and your probe. If you're drilling with drilling mud, it's inside air, and if you're drilling just dry by auger, using auger, you like inflating in air, so no resistance. Second phase, very important, to actually phase pseudo-elastic zone. Different engineers call it differently, it doesn't matter, but this one, elastic linear zone, actually you're getting all main parameters for you, from your Pressuremeter test. And last but not least, its last phase, plastic zone. Why it's important? Because from this zone you are going to get another parameter which is very important for calculation of bearing capacity of your footings. Let's take example. It's very good, very nice, classic example of Pressuremeter test. Very good. So you take tangent to linear elastic zone, you pick up 2 points on this line, and what I suggest you generally, guys, don't pick up like extreme points like this one. Just take 2 points inside this linear line, just to make sure you literally calculating your modulus of PMT. And then your tangent of this line, and you, based on this tangent and the rest of equation you can see, you can take volume of in point A, volume point B, pressure point A, point B. It's what you can see here, like, you know, this one and this equation, and you calculate your all your V naught, its initial volume of your probe, and you this information provided by manufacturer. So they do know length, diameter, VI volume taking from calibration, so I'm not going to discuss in this lecture, okay? And you calculate your Pressuremeter models. Exactly the same approach taking for calculation rebound models. The only thing, you just take your tangent line or secant line to your rebound. So if you have rebound, this one your tangent line. What I suggest is just to take 1 point, some average between these two, like depends how it's happening, and calculate your delta V and delta P. Some people, and you can find it some textbooks, they take initial tangent and then rebound, unload, reload. Honestly, guys, I never ever, like, I didn't understand. It was very difficult, sounds theoretical. For practical point of view, just take this line, okay? And again, rest of calculation exactly the same. Yield pressure. It's very important point, like yield pressure. What is yield pressure? It actually shows you end of your linear portion of the pressuremeter curve. How to do it? Again, you make tangent line. You take the last point at the linear portion of pressuremeter curve. Make projection on your axis of pressure. It's your yield pressure. This parameter used for assessing different types of correlations. There are many empirical correlations, so this parameter very useful sometimes to assess where you're talking about, like to assess what type of soils and etc. etc. You can find it all textbooks, like a lot of information about that. Limit pressure. It's actually pressure that defines failure of your soil. So you actually pressure limits or limit pressure. It's pressure when you fail your soil. And how to assess it? First of all, to assess this limit pressure, you need to know volume corresponding to limit pressure. And what is that? Again, tangent line, your first point of linear zone of this tangent, multiply by 2, and add initial volume of a pressuremeter, V0, we discussed it previous slides. And then you make actually extrapolation of your curve, because generally never ever you can get for the test at this point beyond, it's like imaginary, extrapolated line, and projection from this point of your volumetric with your curve, pressuremeter curve, projection on pressure axis, getting limit pressure. It's a very important parameter. You can use it for calculation bearing capacity of your footing. There is another techniques to assess your limit pressure, and here very important, you need to use pressure beyond yield pressure. Do you remember we discussed previous slides? Why do you need yield pressure? To assess, to using different techniques, your pressure limits. Again, so what you're doing, you take all these 5 points from previous slides, make scales of inverse volume in logarithmic scale and pressure for the same points, and make tangent to these 5 points. Then again, we need volumetric volume corresponding to pressure limits, as whatever we discussed previous slide. You take this volume, make projection on the line, and projection from point C, intersection this volumetric volume and the straight line to pressure scale, you're getting pressure limits. Okay, right now we're going to talk about K0 value, very important parameters or coefficients which used for calculation lateral stresses for your geotechnical calculations. And like you can see notations, the only issue with K0 test when you're using pre-bore pressuremeter, you can get different horizontal stresses, and we're going to discuss it a bit. About sigma not vertical, it's like a normal or burden stress, you calculate standard approach, geotechnical engineers know very well. And because sigma horizontal getting 3 options, you can get absolutely different K0 values. Let's see. First of options, you can take tangent line to initial pressuremeter curve, and last point on this initial portion, touching your tangent line, projection on the pressure scale axis, it's your sigma 0 horizontal 1. The second approach, 2 tangent lines, intersection, you take projection bisect on the curve, pressuremeter curve, and this projection getting another point, and projection on the axis of pressure, you're getting sigma 0 horizontal 2. And the last not least, you just take tangent line to the curve, The first point, do you remember we discussed about the previous slides like VA for V volume, when it's like first point on the linear portion of this curve. Again, projection on the pressure axis, and you're getting sigma 03. You can see how much difference can be from 3D approaches. Personally, if you ask me, I would prefer option number 2, to tangent lines. And I can tell you guys, many engineers, I don't know how many, we have discussed with different engineers, some of them don't trust at all, cannot value from pre-board pressuremeters. It's it's already different arguments, different engineers can have different equations, approaches. What I just showed you, what I found in the books, okay? And Young models, actually, its Young models is going to be used for settlement, for calculation settlement of your footing, and it's pretty straightforward. So you take your E naught, whatever we discussed before, E naught or EPMT, you divide by alpha coefficient, and you getting your Young models. So E naught divided by alpha coefficient, and this Menard made like this empirical in 1962. Menard made this correction factor. This one from one source, and this one from another source. So low table is from Menard manual 1975. You can see a little bit difference. For example, in later version, you can see alpha coefficient for pit, but again, like I am not sure, pit every time normally consolidated. But again, it's like semantic question, guys. We can discuss forever, but never ever used in original tables. What interesting stuff, later stages, Menard didn't include for bedrock alpha coefficient, but it was in text. So he actually later textbooks just made it in table. And what the interesting stuff, original translation was wrong. So I just found it like when I talked to my friend Louis from TextRock, Rock Test company, and turned out hey, it was just wrong translation. Guys, it's sealed. It's not aluminum. Just keep in mind, if you found some books or manuals, it's written aluminum, it's just wrong translation. Correct translation, it's sealed from French into English. And thank you very much for your watching this video. I'm going to make soon a website and going to upload different types of my presentations. And I'm going to do presentation part 2, practical example of the pressuremeter test. Thank you very much. Have a nice day.